Hello everyone, my name is Zhao He. I'm from Tsinghua University. It's my pleasure to be here. I'm going to represent my team and introduce our work, FasterMoE. Pre-trained models are the most popular deep learning models in recent years. They are showing strong capability in multiple disciplines, including reading comprehension and conversation, which are traditional NLP tasks. They are also being used in phenomenal analysis, computer vision, and many other fields. Let's flash back to 2018 and look at the first popular pre-trained model, which was called BERT. It has 24 transformer blocks with a parameter size of 340 millions. It involves massive computation load for each input, but it has outstanding model capability in multiple downstream tasks. Then 2 years later, we have G-Shard. G-Shard is 1,800 times larger than BERT, and it has 600 billion parameters. Significant improvement in model capabilities observed for G-Shard. While G-Shard is only 1.5 times deeper than BERT, it adopts a new structure called the mixture of experts. It employs 2,048 experts in every MLP model, which makes the model size much larger than before. Let's have a look at how MOE structure enlarges model size. First, we have a small model trained with some training data. It has limited capability. If we simply enlarge the geometry of the small model, we obtain a typical dense large model. It involves too heavy computational load that we cannot train it in limited time and computational resources. In the MOE model, the mixture of experts, where expert stands for a small model, and we build a special module called gate. The gate is responsible for selecting a few experts for each input. So the size of the model is enlarged because we can employ multiple experts. And as different experts have expertise in different fields, its capability is very strong. However, as only a few experts are activated for each input, the amount of computation remains small and we can train it in limited time. To train MOE models in distributed systems, we adopt a special parallelism method called expert parallelism. In expert parallelism, both experts and training data are distributedly placed on all workers, which means on different workers there are different inputs and different experts. As I mentioned before, the gate selects a desired expert for each token. So we perform an OTO communication to send all tokens to the worker where their desired experts are placed. Then, at the place where the experts are placed, all the tokens are processed. After that, we perform another OTO communication to send the output to the original place where the input was placed so that they can be used in the following non-MOE layers. For example, the attention layers that requires the sequence structure. In this paper, we first identify three different challenges in training MOE models using expert parallelism. They include load imbalance, inefficiency in core screen operators, and network congestion. Then, we propose three different optimizations to cope with the different challenges. They include expert shadowing, smart scheduling, and a topology-aware gate. Finally, we introduce a roofline-like model to characterize the workload of distributed deep learning, and we show that this roofline model can guide our optimizations. The first challenge is load imbalance. We train real models to observe the assignment between tokens and experts. The pie on the left shows the situation in an iteration. It suggests that expert selection can be severely imbalanced. The gray expert takes almost half of the tokens. And this is only the situation in one iteration of the first 500 iterations. we can observe that the distribution changes very fast between iterations. To make it even worse, after 10,000 iterations, the situation is totally different. Some experts become more popular while others become unpopular. So the skill varies throughout the training process and it is highly dynamic. We use the example of three workers to illustrate our idea of expert shadowing. In this case, expert 1 is very popular, which means on each worker there are a lot of inputs that desires worker 1's expert 1. So after the O2O communication, there are a lot of input on worker 1 and expert 1 has to process them all. So worker 1 becomes the struggler and the end-to-end latency is very high. Our idea is that instead of sending input to worker 1, we broadcast the parameters of expert 1 to all workers, and we call expert 1 the shadow expert. The benefit of this is that we no more need to perform computation on worker 1, and all the computation for expert 1 can be performed locally on each worker, so it becomes more balanced and the end-to-end latency may be lower. To select the experts to be shadowed, we build a performance predictor. Due to limited time, I'm not going to go deep into this, and if you are interested in this part, please refer to our paper. The second challenge is the inefficiency of coarse-grained operators. As I mentioned before, training an MOE layer involves two O2O communication operators and a computation operator between them. So, if we are using the collective communication operators of O2O, there is great hardware idling. When we are performing the communication, the computation resource is idling. And when we are performing computation, the communication resource is idling. As a result, it's always some hardware idling, and it's a great waste of resources. So we first have to break down the O2O operation into smaller operations. Here, let's take a minute and have a look at the pairwise exchange algorithm for O2O. It involves n steps if we have n workers. At time step I, worker j will do the following things. It sends the data to worker j minus I, and it receives data from j plus I. On the left is an example of 5 workers. At time step 0, every worker sends data to itself. At time step 1, worker 0 will receive data from worker 1. And at step 2, it receives from worker 2. Step 3 receives from worker 3. Step 4 receives from worker 4. Finally, after all the steps, worker 0 has received the data from all other workers, and it is the same for other workers that everybody receives data from everybody else. To schedule everything in a fine-grained style, we first have to split up the tasks. Let's take a situation of 3 workers, for example. The expert on worker 1 has to process input from all other workers. First, every worker has to send its input to worker 1. This is a part of the first O2O, and we call the send process from worker I to worker 1 as I. Second, on worker 1, expert 1 will process input from other workers, and we call the process of input I, Ci. Finally, all workers have to retrieve the output from worker 1, and we call the retrieve process of worker I, Ri. This is a part of the second O2O operation. Now we have multiple fine-grained operations, and we are going to reorganize them into an efficient schedule. We have to satisfy quite a few dependencies between S, C, and R operations. The first baseline of feasible schedule is that we can follow the pairwise exchange algorithms to reorganize the S and the R, and we execute everything in a sequence. This is feasible but poorly efficient. Then we found that we can lower the latency by performing all C and Rs as soon as possible. Here, we still leave only one communication operation happening each time because we don't want to introduce contention in the network resources. To minimize the latency and maximize the efficiency, we are using a group of workers instead of single workers as the granularity of tasks gets split up. Also, we minimize the first S and the last R to minimize our overhead in the schedule by our grouping heuristics. More details of this part can be found in the paper. The third challenge comes to the congestion on the cross-node connection. Commonly, the workers are organized in a tree-like topology. For example, when we are using GPUs as workers, the GPUs within a node are connected with much faster connection. And if we have to send data from one node to another node, the network is much slower than the GPU connection within a node. However, with unconstrained expert selection, there are much more data to be sent across the upper level network. And as a result, the upper level node network is congested. Our solution is that we design a topology-aware gate. Our gate modifies the strategy to select experts. We limit the number of tokens to be transmitted so the upper level links according to its performance. And we redirect the overfilling tokens to the experts on the local nodes for better data utilization. As a result, there are more tokens to be transmitted across the local fast network, and the end-to-end latency is reduced. I want to highlight that we show our design of a specific topology-aware gate to show the methodology of co-design of model developer and system developer to both keep the quality of the model and improve the training efficiency. Different topology-aware gates shall be designed for different scenarios. Now let me introduce the DDL roofline model. It's a roofline for distributed deep learning. We define the x-axis as RCC. It's a ratio of computation latency to communication latency. Here, communication latency takes the place of memory access in a traditional roofline model because it is a key factor to the performance in a distributed deep learning workload. And our y-axis is the same p bar, the per accelerator computational throughput, which is the target that we want to maximize. We have the first roof line as the reference line. It shows the ideal case that the computation and communication are perfectly overlapped. When RCC is larger than 1, which means we have more computation latency, we can overlap all the communication latency and achieve our peak performance of the accelerators. We also highlight a semi-ideal line, which means that communication and computation are performed sequentially without any overlapping. This is a common case in our commonly used deep learning frameworks like PyTorch because there is not an automatic overlapping mechanism and all operations are performed sequentially. Here are a few cases of distributed deep learning workload on the roofline. First one is the data paradigm for MOE models. It's on the lower left part of the model because there are too much communication overhead for the gradient synchronization. Because MOE model is sparsely activated, the computation load is relatively small and it cannot achieve high performance due to limited RCC. But a good point of data parallelism is that we can overlap its communication with backward computation, so it can slightly leap beyond the semi-ideal curve. And for expert parallelism, without any optimization, although it has less communication than data parallelism, the load is very imbalanced. So although it's at the right part of this figure, it still has low performance. And as for our optimizations, First, shadowing a few experts can relieve the situation of load imbalance. So its RCC is reduced, but its performance is increased. Then with smart schedule, we overlap communication with computation. So its performance is further increased. And for topology-aware gates, we are reducing the communication volume from the algorithm itself. So its RCC is larger and it can achieve higher throughput. Here are some implementation details about FasterMoE. It is based on a system called FastMoE. It is a PyTorch-based MoE training framework. It is the first framework that supports expert paradigm on PyTorch platform. And we modify the operators and we customize a few gates in FastMoE to verify our ideas. We are using Metron LM as a transformer codebase, and our system is open source at this URL. We compare FasterMoE with quite a few baseline systems. The first one is the systems that support faithfully selecting top K experts for each token, and it does not require modification of expert selection strategy. The first one is FastMoE. It is a baseline of expert paradigm. The second one is from Microsoft. The DeepSpeed baseline is for data paradigm. The MoE model implemented by a single GPU version of FastMoE is parallelized by zero optimizer stage 3 to fit into the limited GPU memory, and it is the same memory footprint as expert paradigm, and this is the only way to train the large MoE models. The second type of system is systems that require specific expert selection method. The first one is G# from Google. It employs a capacity mechanism for each expert. It limits the number of tokens going to each expert and drops the rest of them. Unfortunately, this baseline is only available on TPU platforms, and we don't have access to any of them. Luckily, in FastMoE, it is implemented as a customized gate, so we use that one in our experiments. Another baseline is Thick and base layers from Facebook. It runs a matching algorithm over the match score matrix of input and experts. It seeks for a perfectly balanced assignment with that algorithm. For evaluation setup, we have two clusters. The first one has 16 V100 PCIe GPUs, and the second one has 64 V100 NVLink GPUs. We train in total 7 models of different sizes, and we want to observe the performance of different systems in different use cases. First, we do a case study of expert shadowing. We observe a model of 16 experts in 60 iterations and see whether the experts are shadowed. Here, the black blocks means that the expert is shadowed in the iteration and the white length means not. We observe that in different iterations, different experts are shadowed dynamically according to different inputs. And on average, 19% of the experts are shadowed. As for end-to-end latency, we found that up to 1.97 times speedup is observed in one iteration. For smart scheduling, we first estimate the theoretical upper bound of this optimization by our performance predictor, and we found that there is up to 1.71 times speedup that can be achieved in theory. Then actually we achieved 1.42 times speedup, and the effectiveness of this optimization varies from different models, and it shows more effectiveness in the larger models. For FasterMoE with only expert shadowing and smart scheduling enabled, we compare the speedup over FastMoE and zero optimizer because all the systems run the completely same workload. And we found that more than 17 times speedup is observed over deep speed plus zero optimizer baseline due to the nature limits of data parallelism. We also achieved more than 5 times speedup over FasterMoE because of our optimizations. To compare with G-shard and base layers, we train real models to convergence and observe the convergence speed. We find that both baseline systems take more steps to converge, and our system has a convergence speed 1.37 faster than G-shard and 2.19 times faster than base layers. Our topology aware gate makes the iterations 9.4% faster, which means that it effectively reduces network congestion. Finally, let's conclude the system in a nutshell. The MOE models are large and dynamic. To train the MOE models with higher efficiency, we first introduced expert shadowing to relieve the load imbalance situation. Then we use the smart schedule to overlap the computation and communication. Then we design a topology-aware gate to reduce congestion in the network. And all above optimizations are guided by our DDL roofline model. That's all of my presentation. Thank you very much. And if you have any questions, don't hesitate to email me. You can also post issues on our GitHub repository. The links are shown on the screen.